Hello, everyone. Welcome to week 11 of this course. Um, this week, we're going to look at lab 12 on diode characterization. And if you're wondering if you're watching the correct video for this week, then you are. Um, we are just skipping lab 11 for the semester, and we're going directly from lab 10 to lab 12 this week. So, as the title suggests, this week's lab will be focused on measuring the diode's characteristics. And diode is a new device that we're exploring this week. And as such, the first thing that we should ask about any device is what are its IV characteristics? And that's what we're going to do in this lab um, is design a test setup that measures the IV characteristic of a diode. Um, the second objective of this task is to use the characteristics that we have measured in the previous task to predict the operating point of a DC circuit with a diode in it. And for this, we will use something called the Loadline analysis uh, to make that prediction. And then obviously to check it by constructing the circuit. Okay, so the first question for today is, what is a diode? A diode, it's a circuit element which is characterized by its exponential current voltage relationship. So we've seen devices like resistors, which have a linear IV relation. We have seen capacitors and inductors, which have a differential IV relation in time domain and a complex IV relation in frequency domain. Now we are looking at this new kind of device, a diode, which has a nonlinear and particularly an exponential relation between the voltage across the diode and the current through it. Okay, so this is a typical curve that you're seeing here for a diode. Um, yeah, so now what are the implications of the diode IV relation being exponential, right? So the first thing that you should notice about this curve is that it is not symmetric in voltage, which is to say applying a positive voltage across the diode versus a negative voltage does not result in the same current, right? That was uh, resistors, capacitors, and inductors. They were all symmetric devices, right? Except for maybe polarized capacitors, electrolytic capacitors. So that's the first thing you should notice, and that basically means that the diodes are directional devices, and by that I mean uh, if the diode is meant to be placed in certain orientation in the circuit, then you cannot get the same result by flipping the diode around in the circuit. And the second implication or observation you should make is that the current voltage relation is now not linear; it is non-linear, and so the very useful theorem of superposition will not apply generally, right? And it's easy to see on the diode curve itself. So for example, if I have a 1 volt source attached to the diode, then superposition says that I can break that up into two half-volt supplies and then measure the current through the diode due to each half-volt supply and add up the current to get the um, response due to the full 1 volt, right? And if you look here, due to half a volt, this is the current that results. And due to the two half volts, it's the same current. And if you add those two currents, like superposition says, you only get this voltage. But if you actually apply the full 1 volt, you get a current that is different from the sum of the two currents, right? So that means that superposition no longer holds. And so we have to be very careful in analyzing circuits with diodes. And uh, naively and don't naively use superposition without um, making a few changes to correct this. Okay. So diode circuit symbol, just like the diode itself, is also not symmetric, and so it must be connected the same way as it is indicated in the schematic um, on the actual circuit. Okay, so a diode symbol consists of this triangle with a um, dash in front of it, and this triangle shows the direction in which the diode will conduct current. Right, so in physical devices also, the directionality is usually indicated by a silver line or a black line like this to indicate the cathode. Okay, so if on the circuit schematic, this dashed line is connected to ground, then we better connect this end of the diode to ground and not this end. Okay. So with diodes, we'll hear this word bias a lot. Um, and the this word is basically describing how the voltage is being applied, um, whether a positive voltage is applied or negative voltage is applied across the diode. And the convention is always to describe it as a positive voltage if the cathode is at a lower potential. And if the cathode is at the higher potential, then we call it a negative voltage, right? And and the positive voltage across the diode is also described with this term called forward bias, and the negative voltage is described as a reverse bias condition. Okay? So when the diode is in forward bias or a positive voltage is applied across it, it conducts current, whereas when it is connected in reverse bias, it does not conduct any current, as it was evident from the IV curve of the diode. Okay, so let's look at some diodes and circuits. Now, the first thing to keep in mind is anytime you construct a circuit or design a circuit with a diode in it, you should always have a current limiting resistor in series. Okay? And the reason is diode currents are exponential in voltage. So if even if some small noise kicks the voltage up a little bit, that can exponentially change the current in the circuit. Say if you design the circuit for 10 milliamps and you made a small change here, then then you can change the current through the circuit by factors of 10, right? So you can change the current through the diode drastically. And to avoid that, and to avoid overcurrent in the circuit, you should always use a current limiting resistor. And what that does is basically, as soon as any change in the circuit tries to run more current through the diode, that results in a larger voltage drop across the resistor, and so the voltage across the diode is limited, and so the current through the diode is also limited. Right? So basically, this provides sort of a negative feedback so that any change in the current does not cause an exponential increase in the circuit current. Okay, and in order to size this properly, we need the knowledge of what kind of voltages are being applied, what is the desired current limit we want to set, and also some general characteristics of the diode itself, right? Okay. So yeah, these are quite important and you should never miss them. They're so important that some manufacturers actually build the limiting resistor, current limiting resistor into the device itself, in case some engineers forget to populate them on the circuit. They don't want the parts getting burnt due to overcurrent and heat. Okay, so now we've put diodes in a current with a resistor through it. Let us try and solve this circuit. Okay, by solving the circuit, I mean trying to find all the voltages and current in the circuit. Okay, so in this circuit, the only unknown voltage and current is the voltage across the diode and the current in the loop. So the first method we can employ to find the voltage and current, this voltage and current is analytically. So first thing we do is look at the relation between ID and VD from the diode's perspective. And what it says, the diode IV relation says is that the diode current must be some constant times exponential of VD, right? So let's say that we know all of our diode characteristics. So that means we know this I naught and K. Okay. Second thing, second relation comes from the source's perspective, right? So if there is VD across the diode, then the current being supplied by the source has to be Vs minus VD divided by the resistance, right? And now we have two equations and two unknowns, and so we can solve for it. We should be able to solve for it. So now I'm just gonna equate these two together because they're both the same current. And basically, we end up with one equation in diode voltage. Everything else here is known. So these are diode parameters. These are circuit parameters that we know. But still, this is an exponential equation, and it is practically impossible to solve it analytically. Okay, this is a class of equations called the transcendental equation, which does not have a closed form solution. You can employ numerical methods to make a guess about what VD should be, and then go back and forth in calculating VD and ID from these two equations and get to a close enough solution, but that's quite tedious, right? Obviously, you can use your calculator to ask your calculator to give you the solution to this equation, and it probably will give it to you. But the main point here is that this is an equation that we cannot get a closed form solution for. Okay, so let's say if we, so what is another method that we can employ? And the other method that we can employ is called the load line analysis. So in this, what we basically do is we plot the first equation from the diode's perspective, right? Which is from the diode's perspective, and that's this blue curve here. And we plot the second equation, which is from the source's perspective, right? Which is this line equation here, Vs over R minus Vd over R. Okay. So the diode in this context is the load for the source, and the source is sometimes also called the source voltage is also sometimes called the line voltage. Right? Deprecated term, but sometimes still used. And so this analysis basically says you draw two lines that describe the voltage and current from the load's perspective and from the line's perspective. And the intersection of the load line is the operating point of the circuit, because both equations are satisfied here. So this graphical method basically involves plotting the two curves and finding the intersection point. Usually, so in this case, I've said that we know the diodes diode parameters I naught and K here, and so we can plot this curve. But usually, even though we know this from the devices manufacturer, from the data sheet, there will be enough variation within the process that you can't be certain of what these values are, or because of the exponential nature, a small change in this value will actually make a difference. And there's a temperature component to this, so measuring at certain different temperatures will result in different curves. So the best way to actually get this curve for a diode is to measure it. Okay, so apply a small current, apply a small voltage, measure the diode voltage and current, and build up this curve, and then you can use this curve to actually predict any um, solution to any circuit that the diode is used in by using this load line curve, right? So I can change the resistor, and that basically will change the slope of this line. Or I can change the supply voltage, which would basically change this intercept. So I can move this back and forth by changing the voltage. But in either case, you can find the intersection point of that line with the load curve, and then find the operating point of the circuit. Now, the third method, and which is probably the most widely used, is the approximate method, right? And in this method, what we basically do is approximate the diode with what we call the constant voltage model. And in this constant voltage model, what we check is whether the diode is forward biased or not. And if it is, then we say that the diode voltage is approximately some constant voltage. Okay, so this constant voltage I've used 0.7 is um, is is very common number, but this will be device dependent, as you will find in task 2. Okay, but 0.7 is most general number to use in this constant voltage model. Right? So basically, after you've made the assumption that the diode voltage is about approximately 0.7 volts, it's quite easy to calculate the current just from the source equation. You subtract Vs minus 0.7 and divide that by R1. That's your current. Okay. So the approximation will be applicable and adequate for most applications. Obviously, like I said before, 0.7 is 0.7 is it will depend on what diode you're using, but most diodes will have a constant voltage value around 0.7. Some Schottky diodes and Zener diodes may have slightly different. So Schottky diodes may have somewhere lower, like 0.4. But then again, it also depends on what kind of source voltage you're using. But the more important thing here is that this assumption of VD equals 0.7 only applies if Vs itself is at least greater than 0.7 volts. Right? Obviously, if this voltage, the source voltage is only 0.2 volts, it obviously cannot create a 0.7 volts across the diode. Okay. So sometimes people will also use this as a criteria for forward bias by saying that since the source voltage is greater than 0.7 volts, only then is the diode in forward bias, and only then that I will use this approximation, diode voltage approximation. Okay. Okay. So next I'll talk about instrumentation amplifiers and why we need to use them. Now, if you're confused about why I'm talking about instrumentation amplifier here, when this lab is obviously about diodes, then you should go back to the lab manual and look at the lab tasks and go through some of the theory section in the chapter to sort of know why I'm talking about instrumentation amplifiers in this lab. So you can pause the video here and so go and look that up. Okay. So now if you know in what context I'm talking about instrumentation amplifier, then you'll know that for this lab, the reason we need instrumentation amplifier is because we want to measure a differential voltage across the resistor. Now you're asking the question, we measured the differential voltage across the resistor in previous labs by directly connecting the oscilloscope channels of the 82 to across the resistor. And you're absolutely correct. With the 82, you do not need to use an instrumentation amplifier to measure this voltage. But you need to be aware that most lab equipments that you will encounter will not have a differential probe like the 82. They will only have a single-ended probe, which means that one of the reference end of the probe is always connected internally to ground. Okay, so chassis ground. So what that means is if you connect that single-ended probe across the resistor, you're basically shorting one end of the resistor to ground, which messes up the operation of the circuit. And so in order to measure differential voltages like that with single-ended probes, one method is to actually use two channels to measure the two voltages across the resistor, both reference to ground, and then take the difference of those two voltages on the oscilloscope using math mode. Okay, or you can export the data and take the difference. The other method, so that's one method, but some oscilloscopes may not even have a math mode. So in that case, you would want just a single-ended voltage to measure. Or in our case, even if the oscilloscope did have a math mode, you want to plot an XY graph, and many oscilloscopes can only plot XY graphs using channel 1 and channel 2 of their input channels. Okay, so in that case, you cannot use the math channel to plot an XY of the current and voltage. And that is why for this lab, if you were working on some lab equipment that did not have a differential probe, you would need to use the instrumentation amplifier. This instrumentation amplifier basically converts a differential voltage to a single-ended voltage that is referenced to the circuit ground. Okay, and so I've given you the answer to probably pre-lab question 1 or maybe task 1. Well, that is it, right? That's why we need to use an instrumentation amplifier. But in our case, since we're using the 82, we do not need to use it. Okay. So the next question, should I understand about instrumentation amplifiers and how to use them? Absolutely. Because, well, there are one class of amplifiers and you need to know what amplifiers are and what instrumentation amplifiers are. And the second is, even in the context of this lab, not all labs will have 82, will have differential probes. So you need to understand how to use instrumentation amplifiers to make differential measurements into a single-ended measurement. Okay, so that is all I had to say about diodes and instrumentation amplifiers. Now let's look through the lab tasks really quickly. So starting with the pre-lab, one thing I will note here is that the pre-lab, again, this time has two tasks. One is simply answering questions based on different references, whereas part 2 involves building a circuit and making measurements on it. Okay, so don't leave this to the last day, because you will need some time getting used to building the circuit with the diode and making measurements on it. Okay, so pre-lab 1, I think question 1 and 2 are pretty straightforward. So you can do that. There are some it references some figures on from the theory section, so you need to look at those figures and make your calculations and analysis based on those figures. Question 3, you have to look up the data sheet of the INA 121. So this is the This is the instrumentation amplifier. And so it's asking you a bunch of questions that you should be able to answer based on the data sheet. So for these two tasks, question B and C, it asks you about the input common mode voltage uh, given different conditions. Okay, so there's two graphs in the data sheet um, that you can use to get the answer to these two questions. One of them is for a supply of 5 volts, the other is for a supply of 15 volts. And on that graph, you can find information on how to read off the numbers for different gains and different inputs and so on and so forth. Okay. Input resistance, again, you can dig through the data sheet and find the input resistance of the plus and minus terminals, or the input terminals of the instrumentation amplifier. So in pre-lab task 2, keep in mind that you are constructing and doing this for 3 different diodes. But basically what you're doing is you're applying a DC voltage 5 volts to the circuit. And this diode, you're going to once measured with the forward bias and once measured with the reverse bias, measure the voltage VA and VB. And from that, you're going to sort of determine whether this orientation is the forward bias or this orientation is a forward bias. You know the answer to that question, but by looking at the diode on the circuit, the cathode marker of the circuit element, you should be able to tell that too. Okay, so task 1 of this lab is simply answering a few questions about the instrumentation amplifier, and as such, it's not an experiment. And so you do not need to include an objective or a conclusion for this task. You can simply just answer these 2 questions about the instrumentation amplifier, and that will be more than enough. Okay, so task 2 is the task here is to first of all design a test set, and then to obtain IV characteristics for 3 different diodes. Okay, so so the design is part of the task, and as such you must document all of your design considerations and calculations and what you end up for the final design. Okay, so this must be well documented and well presented in your write-up. So I have already talked about how to analyze a circuit with a diode. Basically, the topology here is given to you, and you have a sinusoidal voltage source or time varying voltage source. Let's make it like that. A current limiting resistor and a sense resistor to measure current. The diode under test. And that's it, right? So we're designing for these 2 components. This is given to you. It's a voltage source that varies between -4 and 4 volts. And this diode we're going to change throughout our experiment to get different IV curves. Okay, so the criteria to design this is also given to you. We want to design our lim and our sense such that the device current, typical device current, is about 30 milliamps. It's not a very strict restriction. You just don't want to go too high, too much higher than 30 milliamps, and you don't want it to go too much lower than 30 milliamps either, right? So you want your current limit to be about 30 milliamps, okay? And for this analysis, you can actually use the approximate method 3 that I showed you, the approximate constant voltage model to um, sort of get an estimate for what resistors you should use for R lim and R sense. Okay. Okay, so in this task, like I said, you'll be testing different voltages in this circuit. So first you'll be looking at IN4148. So this is a fast switching power diode. Next, you'll look at two of these diodes in series. So when you put diodes in series, you always put them in the same orientation. Okay, putting them in different orientation just does not make sense. And so you will do this experiment with this series set of diodes and get its IV curve. And then you will do the same for the IN 5891, 5819, which is a Schottky diode, and then for an IN 1N 5226B, which is a Zener diode. Okay, so yeah, so that's basically the task here. And you will export the data from the oscilloscope so that you can use it for later. And yeah, so you'll see where you need to use this for later within the task and also for task 3. Okay, so one thing I haven't told you about is the Zener diode. So I haven't talked about the type of diodes. You can look this up on the lecture video and in the lab manual. But one important feature of the Zener diode that I should mention here is its Zener breakdown. So basically, so what I've said so far is that the diodes will not conduct any current unless they're in forward bias. But if you increase the reverse bias, keep increasing the reverse bias, after some point there will be a breakdown voltage beyond which the diode will now start conducting current. Okay, so all diodes will do that. Even the regular PN diodes and Schottky diodes will do that. But for a Zener diode, what is special about the Zener diode is that this Zener breakdown is very clean, and you can make the breakdown is very predictable. Whereas for the Schottky diodes or PN diodes, the breakdown is very noisy and it doesn't allow us to make useful devices with it. Whereas Zener diodes, the breakdown is very clean and you can make useful devices using this feature of the Zener diode. Okay, and so this is one feature of the Zener diode that you will notice here when measuring the IV characteristics of this diode, and yeah, you will see that. Okay, so third task number 3 is, like I said, using the diode's IV curve in the load line analysis to predict the operating point of this DC circuit. Right? So you will calculate the load line. Okay, yeah, so this should actually just say calculate. Yeah, so the line curve, which is basically the current through in the circuit from the source's perspective, right? And then you will plot the IV curves for the two different diodes, the Zener diode and the PN junction diode. And from that, so you'll get a curve like this for PN diode, and then a curve like this for the Zener diode. And then you can draw the line curve here. And from that, you can predict where these two circuits will operate, what voltage and what current these circuits will operate at, given this 5 volts, right? So this should be 5 volts, and the slope of this line will be 1 over 220 ohms minus. Okay, and from this analytical curve, you can predict where the circuit will operate. And then the last task is to actually build the circuit and measure the voltages and calculate the error from what you predicted. Okay, so this error is from what you predicted. Okay, so that concludes the tasks for this lab. Okay, now there is an LT Spice version of the lab for this week as well. Now the pre-lab, yeah, you can do the pre-lab task 1, and task 2 of the pre-lab you can do as part of the actual lab tasks here. But all of the other tasks should be the same. For you guys, the questions about instrumentation amplifiers appears in task 2, so this will not require objectives or conclusions because this is not an experiment. But for all other tasks, you should have an objective and conclusion. Okay. Yep. So these are the tasks are exactly the same as 82 version. You just will be constructing it on LT Spice instead. And yeah, so if you have any questions, do let me know or ask any of the other UTAs. We'll be happy to help you. All right. Good luck.